in automotive electronics, the environment is harsh. Close to the engine block, the temperatures can be really high. In exhaust system, even close to 500 degrees centigrade, and still you need to have some electronics also there, like the lambda sensor, which is measuring the oxygen levels in the exhaust gases. And then in addition to temperature, you have humidity, you have vibration, you have impurities, road salt, and dust, these kind of things. So yeah, I have just one example from automotive that basically what is the challenge from the electronics reliability point of view, and when you need to have, let's say, new functionalities, how the challenges are increased. So this example is a pressure sensor, tire pressure sensor, which basically there was this EU legislation already, I think, close to 10 years ago, that all new cars should have this one, so that the car could warn you if you lose your tire pressure. But there has been a huge amount of technical problems in those systems. So now most new cars have this one, and the system is something like this here. So basically the actual pressure sensor is integrated in the ventile of the tire. And this component the actual component could be, for example, this one here, which is from Infineon. And this actually on the right hand side shows the first prototype, which was developed in Fraunhofer Institute something like 15 years ago. So what do we need for this kind of a tire pressure sensor is, of course, we need the actual pressure sensor, which is the MEMS component here. So there is some membrane which deflects and then that kind of gives you the analog value of the pressure. And when we are measuring pressure, of course, that means that we need to have some kind of a connection to the internal ambient of the tire. So this component cannot be completely hermetically closed. Then, in addition to the actual MEMS component, we need to have the ASIC. I mean, the component which transforms the analog signal to digital signal, and then we need to have some radio part which sends the information to the main brains of the car, so that the system car knows that, okay, what is the actual tire pressure. And now you can already see here that, for example, the connections from the ASIC to the board, they are made with gold wire bonding, and you can easily think that if this kind of a structure is inside your tire, it will face quite a lot of stresses, especially vibration stresses. So therefore, this kind of causes the challenge for the reliability of this kind of a, let's say, highly integrated component. And now this is let's say the current situation, and then where things are heading. This is an example from one of the Infineon engineers visited our lab a few years back, and kind of he said that what is there ongoing, which kind of development there is. So of course the car manufacturers want to get as much data out as possible, for example, for autonomous driving purposes. So if you can integrate something else, then you could get more data out and you can utilize that. So basically, this is the conventional way of having the tire pressure sensor. You could also have some other options like putting the pressure sensor in the rim, or even at the internal surface of the actual rubber tire. And if we would have it here, and then in addition to the pressure sensor, we could, for example, have vibration sensor, then we could get much more out of that. So this is just a schematic illustration that if we could also detect vibration, then when the wheel is rotating, it is in contact with the road, let's say something like a 0. whatever seconds, and then you see some kind of a signal coming from the vibration, which could give you, for example, some additional information like what is the tire conditioning, what is the road conditioning, and for example, what is the friction. So this could be, for example, extremely important in autonomous driving. So one could see, let's say, black ice, and then this car would notice that, okay, now the road surface is very slippery. It could send this information to the other cars, and then they would know that, okay, now we need to decrease the speed or whatever. So here is, for example, their measure data on how this could be signal could be that if you drive with a 50 kilometers per hour in a, let's say, new smooth asphalt, old worn asphalt, or in a gravel, so you get different type of vibration data out, and you can then utilize that one with several different ways. So the point here was that with the higher integration, you might get some added value, you get new data, but also your reliability requirements are becoming more and more challenging. So I think was it Scott who asked in the let's say first or second lecture about this, how you can verify if the acceptable failure rate is really low. So here is just one slide which I stole from my old colleague who used to work in Valmet Automotive in Finland. So he had a presentation of this automotive reliability targets. These really bit vary, but basically we can consider that the lifetime expectation for automotive is typically something like this. It could be a little bit longer, it could be a little bit shorter, and it is how you define it. Sure. So I fully agree with what Samuel wrote in the chat. So yeah, basically, you don't always need to have an additional sensor for that kind of a vibration. Basically, if your pressure sensor is accurate enough, it can of course detect also the vibration. Yeah, that was not my point, that you need to have a separate separate device there or component there. You can also have additional functionalities. Knowing that when the system is more complicated, the reliability decreases. How are we trying to improve the reliability by adding more components, making the whole system more complicated? So that is, of course, the big question. How do we ensure that the cars or whatever electronic system is more reliable, even we are making it more and more complex? And that is the daily challenge for the reliability engineer. So how can we verify that? So of course we have our main tools. They are design, they are the manufacturing, controlling the manufacturing, and then there is the testing. And all these we need to utilize in order, when the system becomes more and more complex and more challenging, then we need to understand all these parts in let's say deeper and deeper levels. So of course accelerated testing is an important tool, but it cannot solve all our problems. So if we make some design mistakes, if there are let's say manufacturing quality things, then accelerated testing is not solving anything. It is just showing us where we are. And this let's say target for 0 defects, that's of course the critical point. So this is as well valid in medical electronics as automotive electronics. So if you really need to go into let's say less than one failure per 1 billion operational hours, or 1 billion devices then it means that just with the classical testing purposes, it's practically impossible. So here in the left-hand side, let's say the idea behind this is kind of try to emphasize. So here we have in the y-axis we have the failure rate. So how many failures per time? And here we have, let's say, different areas. So this is kind of the for example think that consumer electronics or even industrial electronics without safety related functions, we could be here. So we can accept a certain failure rate. So 10 ppms, 10 parts out of million will fail in a certain time frame. Then we have so-called single effects, which means that we can accept one or two or few failures during the lifetime out of large population, but they could be quite costly, but not that costly what we saw from the first lectures. So and there are some tools for this. So for example, design for testing and stress testing and these kind of things. And then we have this, let's say, part where we cannot, let's say, accept any failures. So as said here, and as was referred in these case examples, like Takata case, so if we end up having problems with the safety related features, then the financial stakes are extremely high. So then you need to use these proactive methods, which means that you can, of course, in a complex systems, you can use this redundancy. Like we had this let's say, space shuttle example, so that the ignition, instead of having one ignition system, you have two ignition systems, and if one fails, then the other overtakes that. And that is, of course, network, telecommunication networks. So we have a network which, if one base station fails, then the other base stations can take over. So you still can hear my lecture, even the closest base station would be out of use because there's a next one. Or if somewhere else one is broken, then my voice is rerouted on via some other route to your headphones. So we have this redundancy, but this is applicable only for, let's say, very complex systems where you have enough intelligence in the system that the system really understands that, okay, now some part of the system is out of order, so another part must take over. But then if we think about, let's say, simple electronic components, which are not clever, they are just doing what they're supposed to do, then how do you push the failure rate in quotes below zero? So as close to zero as possible. And this is one way of how in the automotive standards, let's say the quality is ensured. So this is maybe a little bit confusing, but typically we have some specification limits. So this could be now whatever parameter in your component. And then we have the specification limits, lower specification limit and upper specification limit, which means that when you measure something, you measure one component, if the value is either below this one or above this one, then that's a reject. But then we have so-called PAT limits also. So this is part average testing, and this AEC-Q is the automotive standard. So it means that we are interested all the individual components which somehow differ from the actual distribution. So basically these limits here, they are typically defined, for example, so that they are outside the Six Sigma, so outside the deviation of the standard population. So if you would have one component here or here, then you reject it even it is within the specification limits. And if possible, you also analyze the root cause for that specific individual component, because that could have some, let's say, hidden defect, which could then later on cause the failure. I placed in my courses one paper which, let's say, covers a little bit about this area. So showing different types of defects, this kind of latent defects and lethal defects. So lethal defects meaning that you can notice it with something. So it's, for example, short circuit or open circuit, but then you have these latent defects. So you have there, for example, a contamination, which is not directly, let's say, showing complete failure in the electrical performance, but it can during that normal operation then finally end up in producing, let's say, open circuit or short circuit. Okay, sorry, there's maybe I missed the question. Sorry, I meant we are adding a component to improve the reliability, but mathematically that will decrease the one way or the other. So if it's not directly related to safety, then for reliability index, it is always better to add component. Okay, so of course this is you are completely right, and this is the way you need to kind of rationalize. So we could, for example, have a component which somehow controls the reliability or increases the reliability. And if we have this kind of redundant systems, then of course we don't sum up the failure rates, but basically you use it like a parallel system. So like you calculate the parallel the resistance if two resistors are in parallel. So basically then you decrease the failure rate. So that is the same idea behind there. Okay, hopefully I was clear enough with that one. So sorry, two more quick slides on automotive. Then here are some basic, let's say, definitions which are coming from the ISO, the International Standard for Road Vehicles. And why I wanted to add here is that basically automotive is one of the only areas where, for example, when you are considering the reliability, you also consider where the product is going. So you might have different design options for certain parts of the car if the car is sold in a certain part of the world. This is something that is still not, let's say, valid in most of the engineering areas. So, for example, these products, they are identical. There might be some software differences depending on which part of the globe they are sold, but typically the hardware is exactly the same. But in automotive standards, you can basically already in the testing conditions, you can include if you know the data, that what kind of conditions these will see, what type of vehicle. So there might be different versions. These same components could, let's say, go to different types of vehicles and so on. So you can include, let's say, much more data from the actual use conditions. These standards are really, really powerful, and they give you lots of information on the reliability. But what we need to remember is that they are mostly single load tests. There's some combined loading, like vibration plus temperature cycling. But for example, let's say electrical loading is not included in typically in other loads. Like I showed you the example of power cycling and vibration in the first lecture. So these kind of things are not yet included in these standards because it is extremely difficult and it is extremely dependent on the application itself. Then if you have as we all know that we have different types of loads, then how you, let's say, sum up the effects. And there are some tools like Miner's hypothesis. So basically you just sum up the damage from one stress plus an damage from other stress, or you have different levels of stresses, how you sum up those. Let's hope that we will get one practical example in the next part of the course where it is shown how this so-called rainfall algorithm is let's say, working. So if you combine power cycling and thermal cycling or temperature cycling, how you can, let's say, mathematically calculate the cumulative effect. So I have tentatively agreed that we are getting this kind of example from ABB. And then maybe this is what I want to highlight, that unfortunately still our models do not consider the time-dependent material properties. So for example, the microstructural evolution of the low melting point alloys here, meaning solder joints. So as I showed you, was it in the second lecture, the solder joint has completely different mechanical properties when it's as soldered or when it has been used in let's say field conditions for a certain amount of time. So basically for solder joints, the strength is constantly decreasing and ductility is increasing when you are using it in high temperature because the microstructure is changing. So these kind of very, this might sound a very small thing, but when we are thinking about target of this kind of a zero failures, or not only when the product is manufactured, but also after 5 years, 7 years, or even 10 years, then these things, we need to improve our understanding on the effects of these kind of things. Okay, and definitely, again, I spent a little bit too much on this aspect, but we still have plenty of time. So I will very shortly show you just a few slides on medical electronics. So as I said, this is something that with the normal engineering logic, you can, of course, understand what is the challenge here. So for medical electronics, of course, there's, let's say, one important thing is that the devices can be either on your body or in your body. And of course, that's there's a huge difference on the requirements, because in addition to the reliability, you also have the requirement for biocompatibility, so that your body does not harm the electronics, and even more important is that the electronics does not harm your body. So that is, of course, you need to use some tools in order to seal the electronics from your body. And quite often it is something like a hermetic encapsulation using titanium case or stainless steel case. You have, of course, very different types of electronics, medical electronics. You maybe need to regulate your bodily functions. You need to monitor them. You need to enhance them. So, for example, cardiac pacemaker, and you have some devices for your neural system, like integrated pulse generators, which gives, let's say, small electrical shocks to your brains, for, let's say, for example, to decrease the symptoms of Parkinson's disease, and so on. It can be very simple ones like hearing aid, which you put in your ear. There could be only one IC, or then this cardiac defibrillator, which could contain something like 50 integrated systems. And nowadays, of course, these microsystems, the role of microsystems, different types, is constantly increasing, because you want to make small systems, which we can all understand that if we want to put something inside a body, it's a huge difference, which is the size. if it's the size of my fist, or if it's the size of my fingernail, or if it's the size of a, let's say, tip of a pen. So for if you get the same functionalities by having higher miniaturization, the biocompatibility might be easier to achieve with the smaller ones. But of course, there's a huge amount of challenges in the electronics integration. So here is just a few examples on let's say, typical medical electronic devices. And let's have an example here. This is something that we have studied in our lab in one of the courses earlier. So this is Medtronic iTro 3, which is this implantable pulse generator. So this is for example, for Parkinson's disease. So for example, my aunt now has had this kind of a device about, let's say, 4 years or something like that. So because she has the Parkinson's disease. So basically the idea is that this part, the actual device, which is also looks like this here, that is typically put under the skin, either close to your shoulder or on the stomach or even back. And then you have these wires which lead to the electrode, and then the actual electrode is put into a specific place in your brains. And then you have a, let's say, remote controller, which the doctor is programming beforehand, and then you can adjust the electrical shocks when there's more, let's say, shaking, for example, in your left hand. Then you have a certain protocol. So this electronics here gives small electrical shocks to the brain, and then that eases up the symptoms. So basically, it's not healing anything in that sense, but it is easing up the symptoms. So you can basically, the point is that you can decrease the medication, which also has some side effects. So the point what I wanted to highlight here is just two things. First of all, you don't want to have surgery every second week. So of course, this should be something that which can withstand in your body and make the function several years. In fact, my grandmother had this pacemaker, and she had that one for, if I recall correctly, something like 13 or 14 years without any battery change. So it was operational the rest of her life. So it means that you need to have also enough electrical energy in there. So as you can see from here, the battery takes most of the space. So this length here, this is something like 5 centimeters, maybe 3 centimeters, and the thickness is what I would say, a little bit less than 1 centimeter. That is roughly the size of this device currently. And this is the electronics. And when we are considering the hermeticity, so this device is completely covered with titanium. It has a titanium welding. The critical part from the hermeticity point of view is, of course, that we need to get the electrical signals from the electronics out to the wires, which then lead them to the electrodes. So this part here is the critical part. It is covered with silicone, so you can kind of faintly see this little bit darker material here. So that's the silicone polymer, but that's not fully providing the hermeticity. The point here is that how these wires, when they are going through the titanium case, how they have been manufactured. And that is, let's say, relatively complex metallurgy there. So there's a niobium studs where these wire bonds are attached on both ends, and then these niobium studs are kind of sealed from the titanium case. So you have their ceramic bulk, which is soldered with gold on both sides. So you have basically titanium, which is soldered with gold to the ceramic block, and then this ceramic block is soldered with gold tin to this niobium stud, and the electrical connection is going through this niobium stud. So only for one specific small part here, you need to have a relatively complex solution in order to really be sure that this is hermetic and it is reliable inside a human body for several years. So one additional thing which maybe should be mentioned in relation to medical electronics is that as the let's say qualification and verification procedures are extremely tough. I mean that they take a lot of time and money. You need to verify the authorities that, okay, these products are safe. It also means that the technology is developing much lower rate than in other fields. So for example, in fact, this electronics, which is inside here, one could kind of consider it as an ancient electronics. So it has a ceramic board because it's extremely reliable. All the components are very traditional ones. So basically, you could most of the components, most probably you could find in if you open an old radio from 1980s or 70s, you could find the same components there. So because all the new things, whatever you change, you need to go through the procedure again. Also, I have here another example. This is an implantable pump for painkiller. So this is typically used in very severe cases when basically you need to get painkillers all the time. So for example, you have cancer, it is progressed in very far. So basically there's nothing to be done anymore, but you don't want to suffer. So instead of having always being the need to inject the painkiller, you can have an implantable painkiller. So this is put into your body. There's a kind of vessel which contains the let's say opiates, and then the medicine is coming out from here and injecting the painkiller to your body. But the actual pump which is inside here is really simple. It's basically mechanics, as you can see. So took this X-ray picture just to show that, okay, even we have very fancy medical electronic tool. Actually, what you have inside there are these. Okay, now I lost the English word for this kind of structures, but basically it's a mechanical pump which moves like that. There's something which is rotating the battery, and the motor is rotating something, and then the pump goes like this, and then it pushes the medicine out to your body with a, let's say, pre-programmed way of getting the correct dose. Okay, so that was just a few case examples about medical electronics. Here is a table from JDEC, and the only point which I want to show here is highlighted with the red rectangle, is that when we are talking about consumer electronics, especially mobile devices, again, something like these, then even the reliability requirements are typically much less. The use conditions are not that harsh, but let's say the reliability challenge might be that you have quite huge amount of power on hours, even the product life is not that long. So here's just a comparison. You can of course disagree with these numbers, but if you have a mobile phone, then during the 5 years it could be on, for example, like more than 40,000 hours. If you have some automotive under hood application where the lifetime is 15 years, even the lifetime is 3 times longer, still you have only quarter or less than quarter of the operational hours. So if there are stresses coming from the actual operation, the number of cycles might be much larger in these kind of applications, which basically are always on or practically always on, in comparison, for example, with your car, which is there. Typically you drive half an hour, 1 hour in the morning, you go to work, then you drive back home, another half an hour or 1 hour, then you go to the shop, 15 minutes or something like that, and that's all. So you are not operating it 24/7. Of course, now there have been these discussions of the new new cars which could be such that during nighttime they are doing something else than just staying on your yard and so on. But this is let's say something which is possibly coming later. But this was everything which I wanted to say about the consumer electronics part, and then I added one let's say relatively simple paper for automotive and space and of ionics. So if you are interested, just look it through. It is there in the my courses page. So there's let's say newspaper or whatever technical paper on these topics. So what are the typical challenges there? Okay, so now we have basically covered this let's say special viewpoints for a few of the industrial areas. Okay, I will answer on the FMEA at the little bit later. So let's come back. I try to remember to answer on that, but at the end of the lecture, so that we can finalize basically this environmental stresses part. Okay, sorry, I will just put it like this. So a little bit about the environmental stresses in general. So as I said, was it on the third lecture, we discussed about this life cycle, the whole life cycle. So it means that we need to understand the stresses also from the manufacturing step, storage, transportation step. Of course, the use stresses are typically those which have the longest duration, but sometimes these other stresses could be much more severe and important. And then the other thing is that which also I have mentioned several times, is that we have stresses which are either internal or external. And what is meant with here, that external stresses are coming from the use ambient, and internal stresses are coming from the actual product itself. So these could be either coming from the manufacturing, meaning that you have some residues, for example, there, or maybe the most important thing is that you have some power losses coming from the actual usage of that component, or for example, the usage itself. Let's say you have a rotating motor and you have your electronics which is controlling that rotating motor. This motor causes vibration for the electronics. So that also could be considered as internal vibration stress, in a difference between vibration step which is coming from, let's say, if that system would be moving. So if you would have an electronic motor which let's say rotates the wheels of a vehicle, then the rotation of the wheel which is just coming from the actual motor, that would be internal stress. But then if the vehicle is driving on a bumpy road, then those vibrations related to use environment are considered as an external. So of course sometimes this limit here is a line of kind of how do they say, a line drawn in a water, so it's not that clear. But just consider that okay, we have both internal and external stresses. And then we have different stresses, as we have already discussed quite much. And the problem for reliability engineer or design for reliability is that these stresses are very, very rarely individual or even sequential. So typically there is always a combination of multiple stresses, and these are, let's say, occurring more or less randomly. So sometimes you have more thermal loads, sometimes you have less thermal loads, but more vibration loads. Sometimes you have higher power losses. Sometimes you have winter time, you have less humidity. Sometimes you have higher humidity, and so on. So if we would need to include all the possible stresses, then let's say our lifetime equation would be 2 meters long, and we could never solve it. So that of course brings us the difficulties in the lifetime prediction. So when we start thinking about analyzing the environmental stresses, then we need to consider, let's say, first all the possible stresses. And so here is just a list, which basically we should be able to identify those stresses. We should be able to characterize those stresses and also quantify those stresses. So meaning that it's not enough that we know that, okay, there's a high humidity, but we basically know the absolute value of humidity and temperature as a function of time during the whole life cycle. Then that would be identified, characterized, and quantified. So here I have marked or listed a few of those, and let's say with a little bit of wanted to put it so that let's say 4 first are somehow related to temperature. So first we have the temperature range. That means the typical and maximum minimum temperature and typical and maximum upper temperature. So that's the temperature range. Then we also need to know what is the time which the product is spending at certain temperatures. So for example, how long it is going to spend at temperatures above 150 degrees centigrade, above 100 degrees centigrade, below -40 degrees centigrade, and so on. Because in different temperatures, the kinetics are different. So if you want to model something, you also need to know how long you are there. But that's not all. So we also need to know how fast the temperature is changing. Because the faster the temperature changes, the more it is like a thermal shock, which means that the temperatures, we may not be able to assume that the temperature distribution is uniform. And that is causing different type of stress states. And then we need to know that what kind of temperature cycles and what is the number of temperature cycles or shocks during the operational life. So of course in the let's say in the actual conditions, if we have here time and here we have the this is the temperature. So actually the curve is that looks very strange, but you understand my point. So it is something like this. So you have different types of mini cycles, maxi cycles, and then you have, this could be, for example, 24 hours or whatever. So during one day, you have this kind of a cycle, or this could be just one operational cycle, like 1 hour or whatever, and then you have these mini cycles. Then how you quantify all these? So you have the maximum temperature, you have the minimum temperature, you have the average temperature here at high, something like X hours, and so on. So rate of temperature slope. So what is the slope here? So how fast it's going down, how fast it's going up, and then during the operational life, how many of these cycles we have, these maxi cycles and mini cycles. And in fact, the rainfall, which I mentioned, is kind of the way to calculate exactly this. So sorry about my extremely confusing drawing, but maybe cut the point there. So then, in addition to temperature changes, we have, of course, humidity, we have changes in pressure, we have different types of mechanical stresses, vibration, shocks, bending, fatigue, whatever. we have electrical stresses, electrostatic discharges, electrical overstresses, electromagnetic interferences, and so on. We have different types of chemical exposures, so ions coming from use environment or coming from manufacturing processes. We have radiation, we have different types of contaminations like sand, dust, soot, whatever. And then we have the combination of these. And quite often the combined or concurrent environments are more damaging than the cumulative effect of each environment. So as was said there a few slides back, the idea in the AEC standard is that you sum up the damages. So you have one damage coming from the thermal cycling, and you have another damage coming from the vibration, and then the total damage is this plus this. But unfortunately, in reliability engineering, 1 plus 1 may be something else than 2, or it's quite rarely 2. Sometimes it's 3, sometimes it's only 1.5. And that is the problem to really understand. And where it's coming, it is coming from the fact that basically temperature typically has an effect on practically all other stresses. It's quite obvious that we have, when you combine the effect of temperature and you combine that one with the effect of some mechanical stress, then because temperature affects on the mechanical properties of materials, then of course you have a combined effect, which quite often is kind of a, is it not synergetic, cumulative effect is maybe the better word of describing that. Okay. So this is already have mentioned several times, so you need to include also these pre-operational phases. Now, what is then the tool for analyzing this kind of combined loading conditions? There are, again, different approaches, and here I would show you just one case example, which is now coming again from the military handbook. So in military handbook, basically, you have this kind of a checklist of different stresses, and they are, let's say, divided into 2 different sources. So you have the natural sources. So these are basically coming from the use environment, and then you have, let's say, induced sources. So basically, this is the internal stresses coming from the actual, let's say, operation of the device. So there could be, for example, some nuclear radiation or whatever turbulence. Of course, this is limited to some avionic applications. So it does not mean that you always need to go through everything, but still it's a good starting point so that you could at least check all those through. And then when you have identified the, let's say, the relevant stresses, both natural and induced, then you can start considering their combined effects. And MIL handbook has this kind of a table which now directs you in understanding the combined effect of 2 stresses. Of course, we could, in our practical use environments, we could have 3 or 4 or even 5 stresses simultaneously. But this little bit maybe not that high quality. I'm not sure if you can see all those details there. That's not the point. The point is just that we have these induced and natural stresses both in y and x-axis. And then if we combine something, then we have see the cumulative effect here with numbers, and these numbers are, let's say, explained here. So if you see number 1, then it's combined to intensify the mechanical deterioration. So basically, if you have these 2 stresses at the same time, then it means that mechanically the effect is more than 1 plus 1. So let's say low temperature and high humidity, then that's definitely the point is that the mechanical strength is less, because when you go below zero, you get ice formation. Ice causes huge stresses, which can cause cracks, and then your system is mechanically weaker. Other thing could be that you have mechanical vibration, and then let's say solar radiation, meaning that, for example, with organic materials, the UV coming from the sun is breaking the polymer chains, or the bonds between the polymer chains. So if you leave something, let's say plastic outside, like this, what do you call them, which you hang your clothes to dry, these small things which you put on the wire, and the clothes are hanging, you keep them for, let's say, a few years in outside, then they become mechanically very, very weak because of the UV. So you have the combined effect of radiation, solar radiation, UV radiation, and mechanical vibration or mechanical bending or whatever. The same is with, of course, with high and low temperature. So for high temperature, some materials behave too soft. For some materials, again, like plastics, become very brittle when the temperature goes below a certain temperature. So this is just a way that when you have this kind of tools, you can see that what kind of combined effects there could be. There are some, for example, number 5 is weakened effect. It means that if you have both, then the sum of 1 plus 1 is less than 2. So they have weakened effect. It could be something that incompatible or unknown. So basically these things mean that typically you don't have these kind of combined conditions. Okay, but there's of course lots of things which you can also let's say disagree here, but the point is not the details. The point is the idea that you have this kind of a tool which you can utilize to understand the combined effects. Okay, I'm checking the time, so now we have 15 minutes time. So let's go into the temperature a little bit more closely, because as I said, temperature is and is definitely the most important factor affecting the reliability. So there, in every reliability handbook, you can find these kind of statements that excessive temperature is the primary cause for poor reliability or whatever. And if you do proper thermal management, then typically you increase the manufacturability, but you also increase the reliability. So thermal management is really key issue in practically all electronic products. So that's the reason that we should always first start from the temperature, and then we can kind of proceed into the other stresses, because temperature always has the effect on the other stresses, this cumulative effect. And we have these, as already mentioned, these power changes. We have turn on, turn off, let's say, macro cycles, and we have these temperature changes in the operational environment. And the cumulative effect is coming from this, and then the effect of temperature on the other failure mechanisms. And as temperature is the most important factor, then of course, as was shown already in the first or second lecture, the lifetime equations, lifetime estimation equations or prediction equations, they practically always contain this Arrhenius part. So again here, this is the Arrhenius equation. So something or anything which is happening in the nature is somehow exponentially dependent on temperature, and this activation energy term here describes how large is the effect of temperature. So this basically comes back to the, let's say, basic rule of thumb that for reliability engineer, if you can decrease the operational temperature, with 10 or 20 degrees, then you can increase your lifetime or reliability with the factor of 2. That could be something else, but that is the basic idea that, okay, being able to reduce the temperature, operational temperature maximum from 100 to 90, then you end up having, let's say, instead of 20 years mean time to failure, you go to 40 years mean time to failure, or your lifetime is going from 10 years to up to 20 years. Definitely not always true, exactly like that, but the direction is the same. But as this is taken from the if I recall correctly, Tummala's handbook, so you need to really understand this activation energy term is for one single mechanism. So it's only applicable at one mechanism, which means that it's also applicable for a certain temperature range. So we all know what happens to an egg depending on the temperature. So if you keep an egg at, let's say, 37 degrees temperature, you keep it there for a long time, you end up having a baby chicken. If you put it in the boiling water, it's not, this process is not accelerated. So you are not getting a baby chicken in after certain minutes, but you have a boiled egg. If you put it in a frying pan, you get a fried egg. So this is here just to let's say, prove or show that these equations, whenever they contain these parts, they are valid only at a certain temperature range. If you go outside that temperature range, the failure mechanism is changed, then the results what they are giving can be roughly correct, they can be roughly wrong, or complete rubbish, like here. The other thing is that we have a mechanism which is, let's say, happening at certain temperature range, but we also need to understand that some materials behave, their properties as a function of temperature are not linear or not even according to some curve, but they I mean some continuous curve, but they have some, let's say, abrupt changes. And again, our organic materials are problematic with this respect. So here is an example of the let's say, typical epoxy. So epoxy is a material which we see very, very frequently, and not only in our normal everyday glues, like Araldite or whatever you purchase from K-Rauta, but also in our electronic products. So for example, most of the organic substrates are more or less based on epoxies, different type of epoxies. So what is here is that try to show that here we have the dimension change, meaning that, let's say, length of a test vehicle as a function of temperature, and this slope here is defining how much the length is increasing when you change the temperature. So that's the coefficient of thermal expansion, CTE or alpha. And with these kind of materials like epoxy, we have so-called glass transition temperature, where the CTE is changing drastically. So it's said that here below the TG, the material is rigid, it's in glassy state, and there the expansion coefficient of thermal expansion is small. Okay, small for epoxy. Of course, this is 2 times larger than copper, and this is 10 times larger than silicon, but it's still, let's say, small. So the slope is smaller. And then above the TG, it is higher. So it's when we increase the temperature, it starts to expand more rapidly. And now, 2 things. First of all, if we are using this kind of a material, typically we need to stay on one side. So we try to typically stay below the DG, so that we, in the use conditions, we don't go on this area, because then the epoxy would expand much and of course stress the other materials which it is attached to. And the other important thing is, this is, even it is said that the DG is 80.4 degrees centigrade. It's not an exact value. It's a, let's say, transition temperature. So this slope is not, it's not straight line here and then straight line here, but it is slightly changing already. Below 80 degrees, it starts to increase slightly and so on. So you understand what I mean. So this is not exact point. And even more important is that the other stresses like humidity can change quite drastically. So in the third part of the course, when we discuss about plated wiring board, I show you clear examples how the moisture intake affects on this one. Another example is here. Most probably Glenn is going to show this one to you in materials and microsystem integration in much more detail. But what I want to highlight here is just that different materials behave differently. So this is a pressure sensor. So here is the MEMS, and in the packaging, 3 different types of organic materials are used. So we have the epoxy molding compound. So it is behaving quite the same as in the previous slide. The only difference is that now in the y-axis we don't have the CT, we have the modulus, shear modulus, so basically the strength of the material, which is below the DG, the strength is high, and then above the CT, the strength drops to very, very small value. And this is how the epoxy behaves, and the DG values, they are typically somewhere close to 100. It could be below 100, it could be even quite close to 200, depending on what kind of epoxies you are using. Then, in order to allow the pressure to enter the actual MEMS, you need to have something which seals the membrane from the dust and particles and humidity and everything, but still allows the pressure to be sensed. So typically then you have this kind of very soft silicone gel here protecting the actual membrane. And in fact, this silicone gel does not have any exact glass transition temperature. It changes its mechanical properties like this. So it is getting softer and softer and softer when the temperature goes up, but you don't have any let's say, direct line here. So you would need to have, let's say, a polynomial to describe it. And then there's the third one, which is silicone glue, more rigid, but still silicone, which is used to attach the pressure sensor to the, let's say, lead frame, the component substrate. So here also you need to have certain flexibility so that the external stresses are not transferred into the membrane. So that's the reason to use silicone glue. But the silicone glue has this kind of a behavior that typically in silicones, the glass transition temperature is somewhere way below zero, typically something like -30, -40. So it is very soft in normal operating conditions, but then when the temperature drops below that critical value, then this becomes very rigid. And then it is not anymore able to stop the external stresses affecting on the actual component. So now when you think that you would need to analyze the stresses, and based on the stresses, the reliability for certain use conditions, you need to see that in different temperatures, different materials behave differently. And then if you want to accelerate the test conditions, then you need to be sure that for example, you are not going if the use temperature is -20 to 80, then in the acceleration testing, you cannot go to -40 if this is -30, because then your material would behave completely different. Okay, and then the same with the let's say metals, especially low temperature metals. So their strength is decreasing and ductility is increasing when the temperature goes up. We have, of course, the effect of low temperatures. So as I said, some materials typically become brittle when there's low temperature. Some moving parts, friction might be increased. If you have lubricants, the viscosity might be increased and so on. Quite often, low temperature is not a problem if you don't have the combined effect of humidity, but in some cases, of course. And then you have these changes. You have the thermal cycling, which means that you are going up and down. Different materials expand with a different extent and different rate, and then you provide stresses. And therefore, you have time-dependent and you have rate-dependent processes. So depending on how fast the cycling is happening. So just showing with this one. So if you have a component and substrate which expand, they have different CTE, then depending on the size of the component and how much temperature is changed, these materials, so like here it would be solder joints, these are stretched. Okay, then you have different tools. We'll come back to this one later on, how you can categorize the environments. So this is from I think coming from AGST Bell Labs. So they have categorized these let's say use conditions, for example, the typical minimum and maximum temperatures, typical delta T's, typical on-off hours, how many cycles per year, and typical cycle times. So basically, these would be then used to also design the testing conditions. But I will show you this again when we start discussing about testing. So finally, I would like to conclude here. So what is the basic difference between thermal cycling and shock? So I already mentioned this one. So when we are talking about thermal shock, it means that the temperature cannot even up inside the product when the temperature is changing very rapidly. Typically, there's a kind of definition that when we are talking about dozens of degrees per minute, then we are talking about thermal shock. If it's higher than that, if it's smaller than that, then it's thermal cycling. Why this is important is that in thermal shock, we get more, let's say, warping of the structures. So we can not only get shear stressing like in thermal cycling, but because of the warping, we also get tensile stresses. So tensile stresses are more severe for crack propagation. And that's the reason that we need to understand the difference between shock and cycling, also from the use environment point of view, but also from the testing point of view. But as I said, this is kind of a summary table for the effects of temperature, and we will come back to these issues when we start thinking about the testing part. There would have been a few slides on vibration and humidity, but we are, as I said, we are coming back to those. So I'm kind of finishing now the first part of the lecture, first part of the course here, and then I will come back to the question. So there was one question related to FMEA assignment we are working with now. Should that be a form of a professional report with theory, literature review, references, summary, discussion, conclusions, or just paper with answers? It depends what is your target. So first of all, most of the products that you are working with, you let's say cannot know exact details. So if you take this one, you have quite a lot of material in the internet, but you don't know all the details, definitely. So the point is that you need to have a nice engineering story. So something which is logical, but it does not have to be the absolute truth. You can assume things if you don't know. And now the question is that which is the level you want to go. If you want to get the full points for your individual part, then I would say that you need to go at least a little bit to the direction of professional in that sense, referring your question. So that you need to use references, definitely yes. You need to check, let's say, what materials would be possible for this purpose, what would be their properties, mechanical properties if this is interesting, corrosion properties if that is relevant from the application point of view, what could be the cost, manufacturing cost, material cost, and this kind of thing. And then discuss on your corrective action based on that. You don't need to have this kind of a very formal structure of the report, so that you would have introduction and then materials and methods and results and conclusions. That's not mandatory, or even you don't need to say same things again and again like in this kind of a formal report. But you need to go deep enough so that you can justify your corrective actions. So as this is really dependent on the, let's say, product or device you select, it is practically impossible for me to give a kind of exact answer. What is the level for getting 3 points, and what do you need to get 4 points? It's the big picture. So how deep, how convincing you can be by utilizing the, let's say, relevant material which is available for your justification. That is enough. So I'm not expecting that you know all the minor details related to materials or processes, and that's the reason I kind of said that it would be good to have a device or product which you have some understanding already. Either you have used it, it's a normal product, or you have kind of some experience because of your hobbies, or you are working with that one on some other course, or you have worked it in your bachelor thesis or whatever. Hopefully that clarified the question. And maybe I will now stop the recording because we are already again